So welcome students, and today's class, as we have defined in the, discussed in the earlier video, we are going to talk about the matrix exponential, right? So the matrix exponential, okay. And to do that, what we are starting out with, we defined what norms are. We looked at the Cauchy-Schwarz inequality. Now we are going to define a norm. We want to specify a size of a vector, which is a so the question is this: specify this is not the question, this is our m, okay, m. So specify a size, okay. It's not very mathematical, but you do realize what I'm trying to do. Specify a size of a vector in which vector space? In L Rm Rn. Oh, is it? Okay. So basically we are looking at a linear map from Rn to Rm, and I want to specify a size. Let's say there is a vector in this, any vector of this looks like a matrix n cross m, and I want to specify our size of this thing. So essentially a norm on this thing. Yeah. Okay. So how do I define it? So we define, so given a, okay, is a n cross m matrix, okay. We define norm of a, okay. How do we define it? It is the maximum of ax. See, okay, let me write it down and then I will explain to you. Less than equal a 1, okay. And the how do I put it? Maybe let me put it here with a norm, okay, right. So how do I define this thing? See, essentially x is a vector, a is a m cross n matrix. So x is a vector in Rm, clear? So this is a vector in Rm. See, so for this, x is a vector in Rm, clear? So basically it is a m cross 1 matrix, if you can think of it like this, okay, or an x, and a. So you see the norm, the small detail here is this norm of x is a Rm norm, clear? X is in Rm, so norm x less than 1. How are we defining the norm of a? This norm is a norm in, so basically you see a is a matrix, n cross m matrix. I am defining a norm of that matrix, yeah. So this is a different norm. Norm of a is defined as the maximum of mod ax. See, a is a n cross m matrix, x is a m cross 1 matrix, so a times x is a n cross, so this norm is a Rn norm, okay. So x is in Rm and a times x is in Rn, clear? A times x is in Rn. So I am maximizing a element of Rn, okay, the norm of an element of Rn with respect to the norm in Rn, right? The unit norm in Rn, okay. So maximum of norm x subject to mod x less than equal 1. Is this clear? This norm is a Rn norm, this x norm is in Rm norm, clear? Okay. So I want to maximize, I want to see a is acting on all the elements of x, right? Okay, and it is taking some values. You take, collect all these values. See, this is Rn. Rn, I know there's a vector and I can define the, the size, the norm of the vector. Once I define it, I take all such things, and after that I take the maximum over this set, over the disk, norm x less than equal 1, okay. Now the question is this: does the maximum exist? What do you guys think? Of course it does. So the small remark is this remark: maximum exists. Why does it exist? Why do you think it exists? Because of compactness. Because of compactness, right? Okay, see, you can easily prove that this function x going to norm x, that's a continuous function, and you are actually taking the maximum. So on this unit disk, right, mod x less than equal 1, unit disk in Rn, right? So the maximum exists, okay, and I am just assuming that that maximum is our norm of A, okay, right? Now let's look at some properties. What are the properties? Number one, norm of A is always positive. Of course it is. Why? See, here I am the properties whenever, so I want you guys to prove these properties, okay? I am not going to do this for you. You guys have to do it yourself. But see, here the point is all of these properties are actually reciprocated from the properties of norm in Rn or Rn. Is it clear? Okay, so those properties are getting reciprocated here because of the definition, okay, it's defined it like this. So the one property is getting transferred into another thing, so that is why norm of A is greater than equal A. That is why quite easy to see, okay. And also norm of A is equals to 0 if and only if A is equals to 0, okay. I want you guys to please do it yourself. Don't leave anything, okay. You prove everything, even if it is very trivial, prove it, try to prove it, okay. Number two, so I want you guys to prove, okay, okay, right. So that is there. Now norm of C times A, let's look at this under scaling. What happens? So what exactly what you expect, okay, since this is a norm, so this thing is expected. Number three, of course, the triangle inequality holds. A plus B less than equal norm A plus the matrix norm of B. So this is called a matrix norm, okay. Number four is mod AX, okay. See, okay, one thing I can do here, and this will be better actually. What I'm going to do is, when I'm writing this, let me do it like this. So basically this will denote the norm in Rn, okay, and this will denote the matrix norm, okay. Why I am doing it? Just to avoid confusion, okay, just so you know that there is a difference in all of this. So also have to change this one, no, sorry, I also have to change this one. So this is mod x less than equal 1. This is again m norm, this is n norm, okay. M and n, two different things. So when I'm saying it's not mod, this is basically norm of Ax. This is dominated by the matrix norm of A, okay, times the norm of x, okay. So of course, I mean this all of this holds for every x in Rn, okay. So that is always there. Prove it yourself. Okay, now let me write down two more properties. Maybe I can write it here. The fourth property is norm of AB. Okay, this is definitely not the norm matrix norm of A times matrix norm of B, but this is given by dominated by matrix norm of A times matrix norm of B. Clear? And the sixth property, let me write it here. Okay, I don't want to do it in the next page. A square. So this property, the sixth whole, I mean this follows from 5. This is less than the A square. Clear? Okay, so those properties are there. So please check it yourself. Not very difficult thing to do, but extremely beneficial. Okay, and now also once we have something like this, there is a okay, fine, yeah. So that is what we define a matrix norm like this, okay. So for example, let's look at one example, okay, and I'm going to do the easy example. I want you to do the hard one, okay, which will be in the assignment. So let's look at an example. See, I mean, you see, what is the matrix norm of A? It's essentially the maximum, okay, of mod AX given and sorry, norm X, and norm of X is less than equal, subject to norm X less than equal 1. Okay, so you see, for every every matrix you are assigning a real number, right, a positive non-negative number. So if I am taking A to be 1001, Okay, why? What do you think is the norm of it? It should be one, no? I mean, it's kind of a intuition, right? Okay, so let's look at what is the norm of A. Let's do this. So this is first of all I have to check what AX is. Yeah, let's do AX. AX is 1001. So the this is the identity matrix times XY, right? So that will be given by x times y, right? Now if you take the norm of that thing, that is given by x square plus y square. Okay, therefore maximum of norm x, sorry, mod x, not mod, it is basically norm, but x, that what is the maximum of this thing subject to this x, this is in R2, right? X, okay, let's just take let's not write x, may get confusing. Okay, let me write it as x1 x2, x1 x2, x1 square x2 square. Okay, so x is basically x1 x2. Clear? So this is essentially 1, you can see. Okay, the maximum of this thing is 1. So you see the if you have an identity matrix, okay, then the maximum is going to be 1. Okay, for an arbitrary problem. Okay, so example 2. Now this I am not doing, you guys have to do it yourself. Okay, but for a arbitrary problem, let's say A is A11, A12, A21, A22. I'm doing it for 2 cross 2, you can do it for n cross n also, no issues. Huh? So therefore let's say if you define what AX is, what is AX? It is A11 x1 plus A12 x2 and A21 x1 plus A22 x2, right? So that's the that's the vector, and you take the modulus of that thing. So that will be given by root over A11 x1 plus A12 x2 square plus A21 x1 plus A22 x2 square. Okay, so your job is to maximize, let's say this particular thing is some let's call it a theta. Okay, so maximize theta subject to x1 square plus x2 square is less than equal to 1. Okay, now I am quite sure you guys know how to handle this thing. Yeah, I mean it should you should remember something of similar tune, right? What exactly do you have to do here if you want to do something like this? Basically you can, of course, do it in less than 1. First of all, open set, you find the maximum of this particular thing. Okay, and then on the boundary you can do that, or you can use Lagrange multiplier also. Okay, so you can use Lagrange multiplier. Okay, but I mean, generally speaking, most of the times you do not really need to compute the norm of A. This is just for your information. Okay, okay, so you can of course do that. Okay, now you see, once we have something like this, there is a small lemma. Yes, this also I want you guys to do. See, here most of the things I'm not proving. Why am I not proving this? Because these are very easy thing to see, but it is important that you do it yourself. Okay, that will actually make you more in tune with what is going on. Okay, so if x is in Rn, okay, if x is in Rn, then the maximum of xi, okay, and 1 less than equal I less than equal n, this is always dominated by the norm of x, which is again dominated by sum I equals to 1 to n mod xi. Clear? This is always true. This is to say, so I mean, if you think, I mean, if you want to prove it, it is extremely easy thing to show, right? I mean, please do it yourself. You see, this is just a one component. You are taking one component, each component you are taking the maximum, that is always going to be dominated by mod x. Yeah, And again, this is also the other way is also not very difficult. If you want, you can use induction to do the other way. Okay, that is also not very difficult. Okay, so please do this part. I mean, the other way is basically x square plus y square is less than equal x plus y square kind of thing. Okay. So I mean, please do it yourself. I mean, try and improve this thing. Yes, that's so. But the important thing is what it says is this. See, this is also a norm of x. This is so generally whenever I'm saying norm, I mean Euclidean norm, right? But here this is also a norm. This norm is called as you guys already know. This is called the infinity norm. Okay, norm of x, two norm. So the Euclidean norm. This is the two norm. Okay, so and that is always dominated by x. This norm is the one norm. Clear? So this is always true. Okay, so please check this part. Please check it. Okay, please check it. Okay, so I mean, not very difficult thing to see, so I am going to skip this part. Of course, if let's say once you define a norm, okay, so given a norm, okay, given a norm, we can define the distance function. Okay, the distance between uh, two vectors. So let's say a and b. Okay, as not vectors. I mean, think of it as matrix. Two matrix as this, right? The norm of a minus b. So the distance is defined as the distance between a and b. Okay, you can define it like this. The distance between a and b is given by the norm of a minus b. Okay, okay. And of course, the I mean, if you have a vector, it is given by mod x minus y. So here we just do it like a norm of a minus b. That's the distance. Clear? So once you have something like this, you can talk about, see, distance. See, the whole idea of defining a norm is to define a distance function. Yeah. Once we have a distance function, we can talk about the convergence of sequences. So convergence. This is important. Huh? Convergence of matrices. Okay. So how do I put this part together? See, first thing first, I want to define the when does a sequence of matrix. Okay, so first definition. Okay, so a sequence, of course, an here. Whenever I am writing an, it means a linear map from Rn to Rn. I am not specifying all the time. So let's say am for each. Let's write it an and then write this thing as Rn. Okay, am is a vector from R. Let's write it as Rn, an, and Rn to Rn. Okay, that will avoid confusion. So for each n in n. Okay, so a sequence an, sequence of matrices, that is, okay, this converges, okay, to a limit matrix if, okay, so let's say limit matrix, whatever the limit matrix is, let's say that is an and l, that's the limit matrix. Okay, if the distance between an minus l, this can be made small. So basically this is equals to 0. Okay, as limit n tends to infinity. Clear? So that is the usual definition. So basically limit n tends to infinity, norm of an minus a, that is going to be 0. Okay, or limit n tends to infinity, you can also say the distance between an and l, that is going to be 0. Okay. Also you see, you can talk about the infinite series of matrices, right? Okay, so how do I put it? Like, let me write it like this: an infinite series of matrices, summation an, okay, n equals to 0 to infinity. This converges. Now the question is this: see, there is an infinite series of matrices. Okay, when does it converge? So this converges if the sequence of partial sums, if the sequence of partial sums, summation n equals to 0 to infinity an, okay, converges as n tends to infinity. Sorry, this has to be, this is sequence of partial sum, okay, capital N, as capital N tends to infinity. Clear? That is you can say that summation 0 to infinity an, this sequence, I mean this sorry, this series, okay, infinite series, this converges to a matrix L. Clear? If for every epsilon positive, okay, see, this definition is exactly what we did for real numbers, okay, there's so nothing to worry about. Just let us put it in the framework of matrices, that's all. Okay, if for every epsilon positive there exists capital N naught, okay, such that summation n equals to 0 to capital N n minus L, this is less than equal epsilon for all n greater than equal n naught. Clear? Okay, so basically the sequence of partial sums that converges. Okay, once it does, then you say that the whole series, infinite series, converges. Clear? Okay, now it is easily seen that I mean, let me write down property, or maybe I can write down as a lemma, okay, that a sequence of matrices an, okay, this converges if and only if each sequence of entries converges, okay. So basically what it is saying is, if you want the whole sequence of matrix, okay, n, to converge, then if each sequence of entries, okay, that should converge, and the same holds for an infinite series summation 0 to infinity n. So you realize what I'm saying. See, an is nothing but a matrix, right? So that has some entries, right? So every sequence, so let's say a11 of that thing, okay, so that sequence, if that particular thing converges, so every sequence of those entries has to converge, and then the sequence of matrix converges, okay. So I'm not going to prove it, but the proof involves this. I mean, you have to use this particular property. Okay, you can use this particular property to prove this lemma. Yeah. So we are not going to do that part. And there is another lemma which is very important, and this also I want you to guys to do, because this is involved in the assignment also. It's not very difficult. Okay, but let's just do it. That if summation an, okay, this is absolutely convergent, okay, then the series converges. I am going to define what absolute convergence is. Okay, but before that, let me write down the sequence. So basically, the lemma says that if you want to see whether 0 to infinity a n, this is absolutely convergent or not, the infinite series, it absolutely converges if okay. So if it is absolutely convergent, then the series converges. Okay, if the series is absolutely convergent, it is convergent. Okay, I mean, this is exactly the same kind of thing which we did in real analysis also. Okay, moreover, you have this thing. Moreover, for each m in natural number n, okay, you have something like this. So the infinite, the partial sum n equals to 0 to capital M a n minus L, that is always dominated by summation n equals to capital M plus 1 to infinity norm of n. Clear? So that is always true. Okay. So this is essentially, if you just look at it, this is essentially nothing but a triangle inequality. But here the things are a little tricky because you have to deal with the infinite sum. Okay, but that's basically the triangle inequality. You have to handle the limiting argument and that sort of thing. But I mean, that's the only difference. Okay, so okay, but the thing is, before that, let me write down what absolute convergence is. But you guys already know this thing, right? It's exactly same as real analysis. So definition, let me put it in a small definition. Okay, so summation 0 to infinity n is absolutely convergent if the n equals to 0 to infinity, the corresponding infinite series of real numbers, this is less than equal infinity. Clear? So basically, you see, what is this thing? This is a series of non-negative numbers, right? Non-negative reals. Okay, if this series converges, then this infinite series of matrix, that is absolutely convergent. Clear? Okay, so once it is absolutely converges, then the original series converges. That's all. So basically, if this is less than infinity, then the original series convergent, okay, is convergent, and it converges to some L. And moreover, you have this property. Okay, this is your assignment problem. Okay, and a very, very important problem to work out. Okay, so with this we are going to end this lecture, and in the next lecture we are going to continue study of a matrix exponential.